Welcome to Honors Physics Podcast. This is the waves in classwork. Before we get started, we should probably remember a couple of equations. These will go on equation sheets, but we will put them down for now. The first equation is that the speed of a wave, v wave, that's equal to our distance over our time, which is lambda over our period, but the more useful one is that it is equal to lambda times our frequency. And that gives us rise to a couple other ones. That's frequency equals 1 over our period, and that period equals 1 over frequency. Alright, so in this question we are given the speed of an electromagnetic wave as 3 times 10 to the 8th meters per second. And we're trying to find the number of cycles per second, which is the frequency. In each of these we are given a wavelength of 400 nanometers, 500, 600, 650, etc. So all we have to do is use our equation that says 3 times 10 to the 8th is going to equal our wavelength times our frequency. Again, we're given our wavelength. We have to be a little careful. This is 400 times 10 to the negative 9th because it is nanometers. Right, that n right there means times 10 to the negative 9th, and we're going to multiply that by frequency. So when you divide that out, you end up getting, let's see, it's going to be 4, sorry, not 4. It is 7.5 times 10 to the 14th hertz. Okay, 7.5 times 10 to the 14th. For this one down here, for green light, we're going to do the same thing. It's the same speed, 3 times 10 to the 8th, and that's going to equal 500 times 10 to the negative 9th times our frequency. So we end up with a frequency equal to 6 times 10 to the negative 14th hertz, positive 14th hertz. Just kidding. For orange light, same thing. We're plugging it in here, 600. And we should start seeing some trends that as we are increasing our wavelength, our frequency is decreasing, which means our frequency here should be less than 6 times 10 to the 14th. And it in fact is. It ends up being 5 times 10 to the 14th hertz. And red light, which has the highest wavelength, should have the lowest frequency. After we plug everything in, 650 times 10 to the negative 9th times our frequency. That's going to give us 4.62 times 10 to the 14th hertz. Now all of these can be expressed in terahertz. For example, this one would be 462 terahertz, okay, which is actually the more common way to express the wavelength of, or the frequency of light. For question number 2, we're finding the range of wavelengths for shortwave radio waves, which are given as a frequency of 1.5 to 300 megahertz. So if our frequencies range from 1.5 megahertz all the way up to 300 megahertz, if we find our wavelengths, we should find that these are the higher wavelengths down here for the shorter frequencies, and these are the longer wavelengths up here. So if we take a look, going into 1.5 megahertz, we're going to say that 3 times 10 to the 8th is going to equal, did I say that right? These should be the longer wavelengths and these should be the shorter wavelengths. Sorry. 3 times 10 to the 8th is going to equal 1.5 times 10 to the 6th times our wavelengths. And over here we should get that 3.8 or 3.0 times 10 to the 8th is going to equal 300 times 10 to the 6th times our wavelengths. When you do that, we end up getting that the wavelength here, the longer wavelengths represented with the smaller frequencies, about 200 meters. And over here, it ends up being about 1 meter. So they range from 200 meters to 1 meter. For X-ray waves, we are given a range of wavelengths here. So we're going to do a similar thing. Our wavelengths range from 5 nanometers all the way up to 1 times 10 to the negative second nanometers, which is a very, 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 very small wavelength. So our frequency is going to vary accordingly. These should be the higher frequencies. Sorry, these should be the lower frequencies. These should be the higher frequencies over here. So 3 times 10 to the 8th equals 5 times 10 to the negative 9th times our frequency. And then over here, 3 times 10 to the 8th is going to equal 1 times 10 to the negative second. Now this is nanometers though, so we need to multiply that by 10 to the negative 9th again. And that's going to be multiplied by our frequency. So when you do that, we get a lower range of 60 times 10 to the 15th hertz. And up here on the very other end, we end up getting 3 times 10 to the 19th hertz. Very, very high frequencies because these are very, very low wavelength objects. Okay, and remember, high frequencies is lots of energy. For question 4, we are seeing a sinusoidal wave. It's traveling along a string. The time for the particular point to move from maximum displacement to 0 is 0.170 seconds. So if you think about it, if we look at a time-lapse photo of what's happening, it's going like this. Okay, so here is our point right here. Our next location, remember, our point doesn't move side to side, but what's going to actually happen is our disturbance will move side to side, right? So then this comes back here. Our point has now moved to an equilibrium position. For our third location, we're going to have it move down here. And our point is back down to here. And for our fourth location, it's going to move back to equilibrium. Let's see, it's going to look similar to this, except we're going to go down here. And then this will be up here. And then our very final fifth location is back to where we started. So we're going to go up and down like this. And our point is back up here. So what we're told is that this time is 0.170 seconds. But if we want to look for a whole period, we have to go from here to here, then onto here, then onto here, and then onto here. So if we count the number of sessions that we're moving through, we have 0.170 seconds here. We're going to move another 0.170 seconds here, another 0.170 seconds here, and another 0.170 seconds here. That's 4 times 0.170, which is 0.68 seconds. Once we know our frequency, we can figure out our period because frequency is 1 over our period. So we do 1 over 0.68, which ends up giving us 1.47 hertz. And then if the wavelength is 1.4 meters, we know that our speed is equal to our frequency times our wavelength. You could have also used wavelength over period. When you plug that in, we get 1.47 times 1.40, or approximately 2.06 meters per second. Okay, if we head on to the next page, we have a question about how we can use the speed of sound, which is 340 meters per second, to determine how far in miles a lightning strike occurred. So imagine this. Here's my thundercloud, very big, ominous thundercloud. And I've got some lightning, and let's see, what color lightning should we use? I'm going to use some yellow lightning. Okay, my lightning's coming down like this, and it's going to hit the ground. And you're standing right over here, some distance away. And as soon as the lightning strikes, you see it, because the speed of light, v light, is equal to 3 times 10 to the 8th meters per second. So as long as you're less than 3 times 10 to the 8th meters away, you're going to see it almost instantaneously. So you see the lightning strike, and then as soon as the lightning strike, the thunder occurs. And the thunder is sending these sound waves over toward you. And the sound travels at a particular speed. And so if we're trying to find how far in miles, we're looking for a distance. Well, distance is equal to velocity times time, so we should try to find a time. So what we can do is we can see the lightning strike. So we see the lightning first. Then, after that, we count until the thunder comes. Count for thunder. And then our third step is going to be to find the distance in meters. Right, and we're going to do that because we know, say that it occurs for, or there's 3 seconds of delay. That means that our distance is 340 times 3, or let's see, that's going to be 1,020 meters. Right, so every 3 seconds is 1,020 meters away. And once we have our distance in meters, we're going to divide by 1,600 to come up with our distance in miles. Okay, so it ends up turning out to be that approximately every 5 seconds is a mile. So for every 5 seconds that you wait for thunder, it's about a mile away. It's a good thing to keep in mind during thunderstorms. For question 6, we're at a large outdoor concert. We are seated 300 meters away from the speaker system. It's also being broadcast via satellite at the speed of light, and that person is 5,000 kilometers away from the concert. Who hears it first? Well, we know that in general velocity is distance over time. So if we solve that for time, time is equal to distance over velocity. So in blue, we'll have the time of you sitting in the stands, and in red, we'll have the time of the satellite listener. Okay, the time it takes for you to hear it is the distance that you are away divided by the velocity that you hear the noise at, which is the velocity of sound. And for the satellite listener, it's their distance divided by the speed of light. So you are 300 meters away, and we are going to divide that by our 340 meters per second, which is going to give us approximately 0.875. And let's get an actual number for that. 0.882. I lost my red. So for here, we want 0.882 seconds. For the satellite listener, their distance is 5,000 kilometers away. And so they are 5,000 times 10 to the third. And they are going to be traveling at the speed of light, which is 3 times 10 to the 8th. And for them, then it takes 0.016 seconds. So the satellite listener wins. They get a big check mark. And the time delay is, let's see, 0.882 minus 0.016, which is going to give us 0.866 seconds. So with no delay, whatsoever, they hear it first by 0.866 seconds. Okay. For question 7, this is arguably the hardest one on here. We have a well, and our object is falling down a well, so we have a pebble, perhaps, or a stone, I guess. The stone is falling down the well. It's going to go down here. And then when it hits the well, which may or may not be water, I'll pretend like it's water here, we hear a sound that comes up. Right? And the sound is going to fly up like this. So we know that the height of the well is the same as the distance that the sound travels. So on the way down, the height of the well can be given by the free fall equation, 1/2 acceleration due to gravity times the time down squared. Right on the way up, our height can be given by the speed of sound times the time up. So we can just set those two equal to each other. 1/2 the acceleration due to gravity times the time down squared is equal to the speed of sound times the time up. Now in this equation, we know what acceleration due to gravity is, we know what the speed of sound is, but we don't know our time to fall, and we don't know our time to come up. But we do know that TD plus T up is equal to 3. So if I solve this equation for, T up is equal to 3 minus T down, and I can just plug that into this equation here. So I get 1/2 9.8 times T down squared is going to equal 340 times 3 minus T down. Okay, when you solve that, you end up getting that your time down is approximately equal to 2.8 seconds. Okay, 2.8 seconds. And that your time up then ends up being about 0.012 seconds. And from there, you have two options. You can either use this equation up here to find your height, or this equation right here to find your height. Either way that you do it, you end up getting that the height is approximately 40 meters. Okay, and depending on, I use 340 here, but to get these numbers over here, I use 343. So you might get slightly different, but it should be right around 40 meters.